You've heard Dr. Lee introducing the elastomer fatigue method based on the Mas-Fatimi algorithm, and Joshua today will discuss the practical application of the method. Please welcome Joshua on the stage.
Welcome, everyone. As the introduction stated, my microphone right here, I'm giving a presentation today on basically our use of FE-safe rubber to predict the fatigue life of an elastomeric NVH suspension component, and basically more focused on the correlation between the predicted fatigue life and our actual measured fatigue life. Okay. So I'll take just a few moments to, I'm not sure if anybody's familiar with Tenneco, but we'll go into who Tenneco is as an automotive NVH supplier. Also, our use and early adoption. Is that better? Okay. Had the microphone wrong. The internal materials test lab that Tenneco has built to be able to do all of the material test requirements that FE-safe rubber requires. It's an extensive list of newer test methods that's required to accurately predict rubber fatigue. Briefly on our methodology in using Abacus and FE-safe rubber. As my short bio said, I'm the materials manager, so I'm really driving our use from the overall project perspective of FE-safe rubber. I am not an analyst, so I don't have the CAE or FEA experience. So at the end, if there's any questions, some of my co-authors may join me to answer those. And then go through basically the results of our correlation, which were very favorable. So just a moment on who Tenneco is. So we're a Tier 1 automotive supplier consisting of 3 divisions. We're Walker Exhaust, so we're the largest manufacturer of exhaust systems in the world. Monroe Shocks and Struts, our damper division. And then I represent our Clevite Elastomers division. We basically make elastomer NVH products for the light vehicle and heavy truck markets. So we have been working with Dr. Mars as far back as 2009 when Dr. Mars was just starting Endurica, which later became FE-safe rubber. So we have been looking at FE-safe rubber for a long time as the path forward to be able to meet our OEM requirements that during the tech review and costing stage for our products, they basically want to be able to give us either road load data, virtual road load data, or that data reduced into a block cycle test and have our proposed design analyzed and guaranteed that a proposed design will pass the durability requirements. I'd like to take a moment. All of the following slides where I go through the material test methods, these are test methods that were developed by Dr. Mars of Endurica and Kurt Miller of Axle Products. And all of these test methods are available commercially through those 2 companies if you have materials that you need analyzed. So for those that do not do any modeling of rubber, so most modeling of rubber within the FEA stage uses hyperelastic properties. And one of the key aspects of that is measuring all of the strain states in a pure form simple tension, planar tension, equal biaxial extension. Get my laser pointer here. The graphic animation here is our particular implementation of this test, to basically measure pure compression properties. We like to also, although it's not part of the hyperelastic modeling, because of the other material testing that we're doing at this time, we always do a simple compression test that we have some automated batch processing where we use that simple force displacement curve although it's a simple compression button, the states of strain are mixed. So that gives us a very simple part to do some automated correlation that our material properties are predicting the force displacement curves correctly. So getting into more of the new test methods that are required for FE safe rubber. So there is a core fatigue module, and as Dr. Lee during the keynote this morning talked about, measuring the fatigue crack growth rate versus the energy release rate. So this is not an easy test to perform. It's something that we've spent the past 3 years developing the test hardware and software side to be able to do the test, able to do all of the vision processing that's needed to measure the crack length. The basic test procedure, you start at a very small strain level and you ramp that strain in very short time increments, 1 or 2, maybe 5 minutes. And over a 20 to 24 hour test period, that strain is continually increased. So you get a 3 to 4 decade of crack growth rate versus energy release rate. And I show the actual data used in the correlation along with, although I'm going to stay on this slide for a second so everybody can watch this at least twice. So basically what we have on the y-axis is the crack growth rate from 1 e to the minus 6th up to almost 1 e to the minus 3rd millimeters per cycle versus internally we like to think of it as the crack propagation energy. That helps us explain it to some of our product designers a little bit easier versus continuing to refer to it as the unloading energy or the maximum unloading energy. So what you're watching in this video is basically the photograph, the still photograph that we take every 2 minutes at different maximum strains, showing the crack length, which we in Tenneco start with a 18 millimeter wide crack on a 150 millimeter wide planar tension specimen. That 18 millimeters, the starting crack length is insensitive on a planar tension specimen. That represents a commercially available diamond blade that's incredibly sharp that we basically plunge into the material until the blade guard is even with the edge of the material, so we get the same crack length on each specimen. And you've seen this twice now, so the crack basically grows very slowly at the beginning and then speeds up as the strain is increased. So let me go back one moment. Okay. So this fully relaxing test procedure is something that's required on all materials. So regardless of what type of elastomer you have, the fully relaxing test procedure is a required test for FE safe rubber. The next slide that I went to a little too soon is the non-relaxing test procedure. So this is basically to perform on strain crystallizing materials. This measures the effect of the strain crystallization on being able to arrest the crack growth rate. So basically what I'm showing here, typically this test is run at several max strain levels, and once you have achieved a steady state crack growth, you start ramping up your minimum strain, and you basically get what's known as the R ratio, or just the ratio between max and min strain. So because it makes a much better movie, I've shown the maximum strain test that we did on this material. So at a 54% max strain, it starts off growing quite rapidly, and you'll notice that the crack stops growing towards the end of this movie, and that is represented as the R ratio increases. My correlation of the Mars-Fatimi model that's input into FE-safe rubber. So another test that's required is the intrinsic strength. The intrinsic strength test is basically a measurement of the minimum energy required to drive a crack through a single polymer chain. So there is an instrument available through Endurica, and there's also testing available through Endurica and Axle. I'd like to thank Axle for supplying this data that I'm showing here. This is one test that we have not implemented internally at Tenneco yet. So in this particular case, we get a measure of approximately 29 joules per meter squared. And so this effectively represents the threshold energy that if the energy within the stress strain cycle does not produce that energy level, a crack will not grow. Now getting into really the heart of what FE-safe rubber does is a critical plane analysis. So what Dr. Mars developed and established was that all elastomer materials are full of intrinsic flaws and with the way the stress strain happens, they want to grow upon a critical plane. And per some of the earlier presentations, that may be a topic that's much more commonly known than I realized before I came here today. So on to the abacus analysis. So we take that material data and we will fit, in this case we used a Ogden N=2 fit. This is just showing our fit to our material data. Our hyperelastic test procedures, we have found the best correlation in the pure strain states testing to 85 or 115% strain seem to give us the most accurate correlation to our actual part measurements. Now that strain state's a little bit higher than the part's actually seeing. But that's what gives us the best correlation, and it has really become the standard practice within Tenneco. This slide is just showing our results on one of the uniaxial directions that we did a fatigue test for. 6 pieces of part force displacement, and then the abacus predictions from 2 of our analysts. Very good agreement. So into the FE-safe rubber material definitions. So this is the summary of all of the material testing. So we wanted to show this, so this would be an input deck that if anybody wanted to use these material properties to try to perform their own analysis, you're more than welcome to. There's really nothing from this from this material set that's necessarily special, because without having the formulation of what that is, I can basically tell you it's a 45 durometer natural rubber compound. This slide is showing the strain history that was established in FE-safe rubber. So what we're showing here is not necessarily how you would use FE-safe rubber in practice, but I'm showing this to kind of highlight that our starting part already has several states of strain in the part. So we have the thermal shrinkage from the molding process. So obviously elastomer parts, most of them are thermoset materials. So they're molded 170, 180 Celsius. So you have the strains that are induced from the thermal shrinkage. And then also most suspension bushings get a post-molding forming process where the diameter of the outer tube is what we call swedged. It's basically to relieve what is essentially tensile strains from the thermal shrinkage and put it into a state of compressive strain. For those that do model rubber or work with elastomers, tensile strains are the worst for fatigue crack growth. And then over here we're highlighting, and down here, that the FE-safe rubber routine was only examining the cyclic axial loads in this case. Okay. I need to speed up slightly. So there are 4 slides just like this. Hopefully when you get this PDF, on your computer screens everything's quite readable. I don't think probably too many people can read these top numbers. So we've got our results, force displacement and strain map from Abacus. We have, okay, so that's actually an animation on that slide. Then we have our FE-safe rubber output and our log life. We have our actual test machine. Basically this was a load control test. So we're showing both the load and the resultant displacements. So this is a check of how accurate we were hitting our loads and then what the resultant displacements were. Now, one of the key things in FE-safe rubber and within the theory that's going on is it's taking a intrinsic flaw size, in this case 25 microns, and it's integrating the damage laws, how many cycles it takes to get to a 1 millimeter crack length. Now, you can set the 1 millimeter crack length to higher values, but you have to keep in mind that there's no co-processing going on back with Abacus to put the crack into your hyperelastic model to recalculate what your strain distributions will be around the crack. So once that a small intrinsic flaw of 25 to 100 microns typically starts to grow into the macro crack region without remodeling it in Abacus to input a crack and get how the strains are going to be affected, it starts to become inaccurate. So I'm almost out of time, so I'm going to skip ahead just to the summary table. So we did 3 uniaxial test conditions, radial, axial, torsional, and then a combined radial torsional. And our predicted results, this part, and if you look at the agenda, The original abstract title was a 3-axis fatigue input. We ran out of time with some of our product launches that are going on right now. Our original goal was to work up from the uniaxial to the various biaxial and then finish with the true 3-axis block cycle input. But we did not make it through our planned correlation study in time for today's presentation. But of the 4 cases we were able to do, between our predicted FE-safe rubber cycles and then from the actual displacement or force drop-off curves, our cycle count of earliest initiation or earliest indication of a rate change within the part. To what I just said on the integration from a very small crack to a 1 millimeter tear, many products at a 1 millimeter tear, you won't have enough of a force displacement response change that a test machine is going to be able to detect a crack that small. You know, the wall thickness on this part is 18 millimeters, so a small crack internally of 1 millimeter may not give you much of a force displacement change. So from a durability test equipment standpoint, we can't terminate it at a 1 millimeter tear. But our correlation values, all 4 cases, the actual part lived longer than the prediction, which directionally, to be able to use this as a tool at the quoting stage, that yes, our proposed design will pass a given block cycle, is directionally the way we always want to be. And the parts lived anywhere from 10 to 40% longer than the prediction, depending on the load case. So at least where we are in this stage of our correlation, very favorable results. Any questions?
Thank you very much. Thank you very much, Joshua, for this. Fantastic. It's almost too good to be true, the correlation that you're getting there.
Well, I guess one of the things, because my background's in materials and material science, and I also have a background in statistics. As I've talked to various people about how accurate I think the results need to be, these are promising, but I honestly think eventually we need to be within 10 or 15%. Because the best way to interpret, if I go back a slide, is that each one of these test cases can be thought of as an individual block of a block cycle. So if you have a 6 or 10 or 15 block cycle and we're off by this much per block, that may sum together being off by a factor of 2 or 3 for the overall test regimen. And since most of our OEMs, that test regimen already has 2 to 3.5 lives of statistical significance built into it. So if we're then off by another factor of 2, we may be designing a part to go 7 lives in order to statistically prove it can go 1 life. So it's going to require much more work on how to handle the statistical aspects of how to do the modeling, to mitigate the risk at the design level.
That's an excellent point. Do we have any questions in the room? Okay, I have one, if I may. I think in one of the slides where you discuss loadings, if I'm not mistaken, there was some mention of thermal loadings. Have you considered any environmental effects like ozone or the temperature?
So the FE-safe rubber code is certainly able to take into account elevated temperature, time at temperature, so aging effects. Ozone, since most of the compounds are formulated to be ozone resistant, unless you were dealing with the type of part say, a bridge bearing pad that's got a 50 or 100-year life, where you need to pay attention even more accurately to the effects of really long-term ozone. The material testing that's required, basically everything I showed here, but then at elevated temperature or multiple elevated temperature, and then all of that testing, or a good portion of it, at multiple aging conditions. So once you start to want to model the effects of temperature and aging, the amount of material testing starts to grow exponentially. So we are just setting up, and actually we'll be testing our first complete environmental set of material properties in the next couple weeks. We've had some samples aging for the past 90 days. We have a silicone part that we need to model some very long aging periods. So we're just getting ready to do that testing.
Excellent. So I'm looking forward to hearing from you again next year.
Yes, not these slides, but the overall correlation, because ultimately we need to get to where I'm showing where we've analyzed road load data directly into our model and show that correlation to an actual RPC style component test.
Excellent. Thank you very much.
We have Will here. Can I just... You kind of hurried through some of the last few slides, but I just want to make sure you had a chance to kind of flag up. Not only did you get the lives within 1.4, which I was quite delighted to see. I'm used to seeing, you know, that's a really good. But obviously, you guys have done a lot of work around being very careful to characterize and being in control of your experiments, so I'm sure that had part of it. But I also wanted to make sure you didn't blow by too fast in comparing the pictures that you got of the initial crack to the predicted crack locations.
So thank you, Will. When he flashed the 5-minute left sign, I kind of got rushed. So what I'm showing in these photos is we took the parts, sectioned them, and then actually mixed up some white epoxy that we injected down into the crack, and let it cure, froze the parts, and then polished them to allow us to take some photographs that would show, for the presentation purposes, the crack location much more accurately. Took them into our microscope, measured the crack length, which I'm reporting in the various tables. I did not point out, and thank you, Will, that the finished crack, although much larger than where the integration of the damage wall stops within FE-safe rubber, all of the cracks actually include the predicted crack location. Unfortunately, we were not able to stop the test machine early enough to catch a very, very small crack. We actually had some parts that when we first cut them open, we could see a 2 to 3 millimeter crack. And then when we tried to put the epoxy in and polish them, we actually polished it away. And we're like, oh, I saw it yesterday and now I've sanded it away, so it doesn't make a very good photograph, you know, for the presentation.
We have time for one more question.
Okay, I got a question. I didn't get a chance to hear the whole presentation. So my question may be related to the previous one, but I want to confirm. Okay. So for the polymer, right, once do the cycling node, they will generate heat. The temperature will rise in the within material, right? So my question to you is, during your test and for chicken knife test, and also your simulation, did you consider this material self-generated heat, temperature rising?
From an analysis standpoint, we did not analyze if there would be self-generated heat, but we had infrared thermocouples monitoring the part. The parts never rose above 30 Celsius. Our labs pretty much maintained at 22. So there was a few degrees Celsius temperature rise, which obviously with any dissipative material, you'd have to test it unacceptably slow to get no temperature rise. The material properties between 22 and 30 Celsius, especially with natural rubber from a fatigue standpoint, I guess we ignored those effects. Maybe the correlation would have been slightly better if we would have, but yeah. We made sure we didn't have a temperature rise issue.
Okay, good. Thanks. So when you do the fatigue test, so your test frequency, can you tell us, so what your test frequency?
1 hertz on all of them.
Okay, I got it. Thank you.
Yep.
Okay, thank you very much. Over the years, we have